Right, hello. I'm just going to go over a quick overview of motion graphs today. So there's three types of motion graphs. You've got your distance, time, I just put distance t. You got your displacement time, I just put displacement t. And you've got your velocity time. Let's start with the velocity time, because it tends to catch most people out. So, you've got your v, ms to the 1, t in s. And that is 0. So that means everything above this line is positive velocity, and everything below it is negative velocity. Now you may be asking, how can we have positive and negative velocity? Well, negative velocity occurs when it's going the opposite direction to the original direction of motion, and positive is the way away from it, if you're following the original direction of motion. So let's do a bouncing ball example. So we throw a ball down, it bounces up, and it bounces up, and it bounces up. So it should be getting less. Yeah, sorry about this. It needs to be getting less each time, that's all. Just need to make sure it is. Right, okay. So what I've drawn badly there is the velocity time graph. So this part here, I don't know if you can see that, but if I go straight down, I get rid of this actually. If I go straight down, that's something called infinite deceleration, and that occurs when the change of direction is instantaneous. It just happens to go BAM! Then it goes, oh, it goes straight away like that. Then it's almost immeasurable in seconds. And that's called instant deceleration, and the forces involved would be enormous as a result. F equals ma. So, yeah, the basic principles, and the gradient of a velocity time graph is the acceleration and we can prove this, as we know, the rate of change in velocity is the acceleration. So, rate of change in velocity, time, change in velocity, velocity up the side. So, I've proved it is acceleration. Now, the distance under this is the area under the graph is the area relative to the equilibrium position. So when it gets to 0, it's hit the equilibrium position, if you think of it like that. I'm fairly sure that's the case. So, I mean, if you're wrong, please, if I'm wrong, please do comment, because I'm not 100% on that one, but, you know, just, we can have a chat about it if you want. I'll do a video if you get stuck in any question. Yeah, that's right. Yeah, so the next one we're going to do, so get rid of velocity time, we've done that. So we've got a distance time. Do it in another colour. Distance time. We've got a distance time graph. So you've got D, I just put D and T. Obviously, you should have correct units on these things. So, a distance time graph, we assume that to be 0, and then obviously it's going to be 0 as well. So a distance time graph shows the distance from, distance, the whole journey. It's not relative to anything. So, let's think of a situation actually where we draw a line. Yeah. So a ball getting thrown up, that is. You see where I've drawn an X in the middle there? I'll just move out of the way. So that represents the height, the maximum height. So if I threw a ball up and it came down, the distance wouldn't be 0 because it's still going up and down. But when it's going up, it's going... If you were doing a displacement time graph, then it would be 0 because the amount up is the amount down. where the displacement is 2 times that, so it's going up and then coming down. So the whole distance going up is times 2 by the distance coming down. So that's the maximum height, is where it starts going the other way. But the distance still increases. The gradient should be roughly the same. So that's how we work that out. That is a distance time graph. So let's skip that. Oh, I forgot to mention, the gradient of a distance time graph is speed, because speed equals distance over time, and that's what you get for doing the gradient of a distance time graph. So let's go to the distance one. Now, people often get confused by distance and displacement. Now, displacement is when it's relative to the equilibrium position. So let's draw one. I just put dP is displacement. T, I put it, M is in brackets is what it's measured in, it's S. And that S standard SI units. Now I'm going to draw something here and I'll explain it in a minute. So displacement, well, what is it? What shows distance and direction relative to the equilibrium position. You can't really say much more than that about a displacement time graph. I mean, that there, sorry, yeah, I'll just put an arrow of the line of the object. So it's a ball being thrown up and then caught again. As the other one, for distance, it went up and then carried up, whereas this came up and carried down, because it's coming back into the arms. So if I throw this, oh, not really well, yeah, oh, God, cut it. So it came back in my hands, even it went whoa over there. I'm going to do this to get it right, watch. Oh, damn it. Oh. Right, there we go, got it. So, it came back to my arms, I threw it up, came back down, and it came back into my arms at equilibrium position. So, the overall displacement, so where it's actually, the overall displacement is where it's actually ended up. So if I threw this and it went all the way over there, the distance would be the same as the displacement because it's gone in one direction. Just the band one direction did down the toilet. Anyway, I'm only kidding about the one direction fans. Okay. So then that's the displacement time graph. That's really all you need to know. I have got some questions here, but I currently don't have the time to go through them. But if you absolutely need to go through them, don't bother. Don't hesitate sending me a comment, and I will go through some of the questions I have in the AQA book. And I can definitely guarantee that I'm right or wrong. I'll see you in the next video.